At its heart, physics is about keeping track of things. Things like mass, momentum, and, of course, energy. The most fundamental rule for energy is that it's conserved. For any system, the first law of thermodynamics gives us a simple accounting rule. The change in the system's total energy is equal to the rate at which heat is added to it plus the rate at which work is done on it. This is beautiful, but for a fluid flow problem, like water in a pipe, tracking a specific system of water molecules as it moves and deforms is incredibly difficult. It's much easier to draw a fixed box in space and watch the fluid flow through it. We call this a control volume. So, our challenge is to translate the simple energy law for a moving system into an equivalent law for our fixed control volume. To build this bridge, let's watch what happens over a tiny sliver of time, delta t. At the start, our system of interest perfectly fills the control volume. A moment later, at time t plus delta t, the system has moved. Part of it has flowed out of our control volume,
and new fluid has flowed in to take its place. So the total change in the system's energy is the change in energy inside the control volume plus the energy that left minus the energy that entered.
If we talk about rates of change by dividing by delta t and taking the limit, we get the famous Reynolds transport theorem, tailored for energy. Now we can substitute our original first law of thermodynamics into this expression. Let's break down the work term, W dot on. It consists of several types. First, there's shaft work, from a device like a pump or a turbine whose shaft crosses the boundary. Then there's work done by pressure. Imagine the fluid just outside the control volume pushing the fluid inside. The rate of work is force times velocity. The force is pressure times area, so the pressure work rate is P times A times V. This flow work happens wherever fluid crosses the boundary. To account for the whole surface, we integrate the pressure work term over the entire control surface. Now, what about the energy flux term? Mass in motion carries energy in three forms: internal energy from molecular motion, kinetic energy from the bulk motion of the fluid, and potential energy from its height in a gravitational field. The rate of energy flow across a small area dA is then this energy per mass, E, times the mass flow rate through that area. Now we assemble everything. We have the heat and shaft work terms, the pressure work integral, the change in energy inside the CV, and the energy flux integral. Let's move the pressure work integral to the right side. Notice how both terms are integrals over the control surface. We can combine them into a single integral. Look at the term inside, E plus P divided by rho. This combination, internal energy plus flow work, is so important it gets its own name, enthalpy, labeled H. This gives us the final, general form of the energy equation for a control volume. It accounts for heat, work, energy storage, and the transport of enthalpy and kinetic and potential energy. For many engineering problems, we can simplify. If the flow is steady, the amount of energy inside the control volume doesn't change over time. And if we have distinct inlets and outlets with uniform properties, the surface integral becomes a simple sum. And here it is, the workhorse of thermal fluid analysis. It tells us that the energy we add, as heat and work, equals the change in energy of the fluid as it flows from inlet to outlet.